Okay, so in order to prepare this program today, of course, we worked and planned for a long time, but for family reason, Tingting is not going to be here. And also, so I will speak about this project because I was the project supervisor. And then it's still me after my intro because the second speaker that was coming from Germany actually fell ill. He got a cold and he was not really in a good shape. So we have to miss him presentation. And it's a dear friend and colleague, but unfortunately he cannot be here. And that means bear with me, and then it will not be about me speaking until the end, okay? So thanks for being patient. So Tingting Chen, as you can understand, is actually from China, and we hired them still in COVID time. So we have done all the interviews online, and finally from borders were open, and she could fly to Denmark, and then she's been living in Denmark now for 3 years. And she finished her PhD at the end of 23 and presented in January this year. So she's now the doctor engineer, and that's why the title. And for the moment, actually, we have employed her in our group. So that's about her. And you can see this is at the beginning, and now that's her. She looks like more experienced, right? So there is about 3 years of difference between the two pictures. I thought it was funny. And so she have gained a lot of experience, of course, but also expertise. So she came with a background in manufacturing, to a professional level, as I will show you in this short lecture. So the short lecture is about her project, which is developing problem solving in manufacturing. So there are some methods, but she found one really good way to solve the problem. And the problem is about the presence of oxidation in silicon production. And I will explain that now, what we mean by that. So that's basically the revenue in billions, in this case dollars, in semiconductors. And you see since the beginning, this is the 80s. This has been growing all in all. So semiconductors are basically made of silicon, and that's what is moving everything in the world. You know, your phone, your computer, satellites, everything, trains, planes. And needless to say, all the digitalization goes through the use of microchips. So for this, we need a lot of silicon. So this company, the one that is collaborating in this project, is in this business here. So we can do microchips for everything because we can make silicon wafers, and these are made in silicon. So we need to make silicon as a material. It's not mined, it's made. And it has to be of ultra high purity for everything that is moving, anything you see in the world, from machines, pacemakers, hospitals, you name it. Everything is based on microchips nowadays. So having problems with this production is in fact a problem that has to be solved. We have seen during COVID, there was really a lack of electronic material because the supply chains were very long. We were using them in Europe, but they were ordered from China, Taiwan, for example. And then borders closed down and we ran out. Cars could not be delivered. For a moment, cars could be ordered today, but delivered in 2-3 years. No more sensors. So how do we make silicon to make wafers and microchips? So there is this method, fast with some degree of impurity, or this one, which is slower, but it's the highest quality you can buy. And for it's called high power electronics, you need ultra pure silicon. Now imagine, in order to make this here, and then it's sliced in wafers, takes maybe 40-50 hours. And if there is a defect after 50 hours, so 2 days of deposition, you cannot use it and you cannot sell it. And one of these will cost 50,000 euros. And it is a problem. 1/2 at the time of the project is actually not sold because it has a defect. So the idea is, can we improve the process in a way that there are no defects so we can save a lot of material, energy? Question mark. And the project was about that in essence. So that's a schematic of the machine. And this is a very good silicon material when it's melted and is becoming this ingot, is called, of silicon. And that's a trace on the surface of silicon when the process is going out of specifications. So most probably this process will produce ingot that cannot be sold, because when there is an impurity, then the wafer will be defective and then no microchip can be made. So the question is, how can we find this? So I said, this takes 50 hours to make, and then there is a camera that is watching through a thick quartz window. And you need to find this picture within a video of 50 hours. This cannot be done by any operator that stays there, day and night just watching. It's impossible. But it is true, the company was making the videos, so was accumulating data, but not analyzing the video. They were only discovering at the end with some quality control that the product is defective. So what Tingting made was a piece of algorithm that could load a video, look through all the pictures, because basically a video is a sequence of pictures every X seconds, basically, and find this as soon as possible. And that was the first objective. Once we learn in which conditions we find the defect, the idea is to predict that there will be a defect. So we stop even before. And once we have learned that, the third one objective was reached, is to set up the process so that it's not going to produce any defect. So I'm going to show you a bit part of the solution in the few minutes I have today. But in essence, this is what happens, okay? Yeah, so this is the product. It's called the ingot. Then we have the process. Some random disturbance will happen. We don't, at that time, we did not know exactly what was. And then in the machine, we observe this. And these are the three objectives that I have mentioned to you, so let's go on. So let's see how can we solve this problem. So historically, in manufacturing, even advanced manufacturing, which we have data, the solution is based on a lot of specific knowledge, it's called. But now machines are becoming more complex. They are gathering, in fact, more data, and in principle, you need more and more and more knowledge to do that. So the idea is to use a data-driven approach in which we find correlations by algorithms. And that can be automated and done faster, because just using knowledge, you need a lot of knowledge, human knowledge, time-consuming, it's expensive, and when the amount of data increases, it's just too complex. You will not find that person that's so expert that can solve that problem, all right? Data-driven approach essentially is what we call it artificial intelligence today. And the tools are deep learning, neural networks, these two here. We actually have seen that machine learning is using just neural networks were just too small, so the problem that it can solve are actually relatively small. What we need to use is deep learning, which are basically neural networks with a lot of layers. So if we do this, we can describe what happens, we can make a diagnostic, so we know why something has happened. And then if we have a good explanation of why, we can calculate when it's going to happen. So that's the predictive analytics. And when we know this, we can implement the algorithm, and then we can optimize. Now, these calculations, that's the good news, are basically all based on linear algebra, so they are very fast. Doing all this takes time, but once the algorithm is calibrated, then this one is super fast. So if the machine is working, we can know real time if it's going to be good or not. And that's basically one of the big powers of artificial intelligence, is how fast it is, okay? More problems. Everyone is using AI today, but essentially you don't know what the algorithm is doing. And this is more true for very big systems. And that's the black box. So this may be good when your phone is just checking whether it's you with the camera, with the face recognition, but it's not good when you're operating 100 million euros asset. You really need to know what's going on. You cannot trust AI to manage an entire factory. It's not safe to start, and it's not secure. So the layer we are introducing to do problem solving in manufacturing with AI, it's called explainable AI. So we put a component of physical understanding in the algorithm. And this is what Tingting has done. And that's basically the structure of the HER project. So there has been some physical characterization. I'll show you some pictures. And then the understanding of why oxidation happens, and then the understanding and the coding of that through artificial intelligence. So know what, which is this physical characterization. So we are able, with some dedicated equipment called focus ion beam, we can cut very thin slices of material, and then we can look inside this kind of defects. And you can see here what happens. The material really has different colors. So there is definitely something going on in the composition of the material. And that composition that has to be analyzed. And these are images of the surface. So it turns out that we can clearly see different colors, but the structure of the surface is the same. So there is not really valuable information in here. We needed to go deeper. And that deeper was done by cutting slices of the material. And we finally found some layers formed on the surface. And you see when it's white, there is a very thin layer here, and when it's blue, it's thicker, and when it's black, it's intermediate. And if you see the scale, we are in the tens of nanometers. That difference is very small, all right? So unless you do this kind of analysis, you will not be able to find really the key of the reason why we see different colors. And now you may ask, well, what's with these colors? Is it really a problem? The color is not a problem, but it's the sign that the composition has changed, and this is what's resulting from this chemical physical investigation. So by the composition of this silicon dioxide at very high temperature, we have silicon monoxide, and that oxide is proven to be the origin of the cause of the defect. Now, we need to build the bridge between the physical analysis and the image analysis, because obviously we cannot do this all the time. That takes a very long time. But at least we found out why the defect starts on the first place. Because then with the different colors, we found the different defect on the surface. And from there, we can go on with the image analysis. In very short, this is how it is done. We load the video. We train it with a database of images. and then we can recreate that image to see whether the algorithm, and now this is digitally recreated, is able to recreate reality. And if you do that many, many times, it gets better all the time. It's the process of training, learning, and then validating. So this is the image that we get from the camera, and this is the result of deep learning. So the software, now the algorithm, is able to really understand what type of defect and give you back the same picture, but this time based on calculation. Good. So here we have root cause analysis, meaning we want to be sure that everything that can lead to that mistake is taken into account. And for that, there is a specific workflow. You analyze, this is very well known in manufacturing, you analyze all the sources of errors, you classify them, and then you look for trends. So here we have our data space, and here we have our types of oxides, and we want to build that bridge in a reliable way. And when we are able to do that, then we have explained how the algorithm works. And this is done in this way. So we can apply it, in this case, any model. At the end, it's data. And then, specifically to our case, we have a way to verify that. And in essence, you know, all this work is just to show you this chart. Meaning, when we use our methods, for example, experimental methods with the orange line, which is the moisture content, the one that will give you oxidation, and then the model is able to reproduce that to a very good extent. So the correlation here is pretty good. It can be improved, but it's only a matter of time. The more data, good data you give to the model, the better the prediction will be. But this is the level that's been reached. Now that we have an algorithm that can predict that, this is the idea. There is a camera watching the process, and then the algorithm is analyzing now in real time the video, and it can tell you whether the process will fail. So you can stop after 1 hour, you know, no need to go on. There has been already oxidation, so you don't need to wait 50 hours. Yes. So in summary, basically those 3 ideas has been formulated and then implemented. So a clear understanding of why defects happens, and then create that correlation between the cause, which was related to moisture presence, and having an algorithm that can detect that through video images. And because, as I said, these models are very fast, now it can be done real time. So we were the supervisor, myself and my good colleague Matteo. Topsil is a Danish company. And then, of course, we had a lot of support throughout the project from all the partners. And so thank you, especially thanks to Tingting that did this very, very good research. Thank you.